Welcome back, students. In the previous video we talked about interference of waves. We didn't talk about light waves in particular, but we generally talked about interference, and in fact we demonstrated interference with water waves. So we didn't even talk about light waves in great detail in the last video, and that is what we'll do now. But I want to recapitulate what we discussed so far. The first point is that for you to observe the interference pattern, the light must be from coherent sources. What are coherent sources? Well, the sources must have the same frequency, and then they must interfere each other or superpose at a constant phase difference. The phase difference must be constant. Then you can observe interference patterns. If the phase difference is not constant, then you cannot observe the interference patterns. So we even had an expression for that. We said, if this is S1, source 1, and this is S2, and then if we take a random point in space, say P, and then we want to find out what the intensity of light at this point would be, then I need to worry about the phase difference between them. Basically that actually comes from the path difference. From the path difference I can find the phase difference between these two waves, the angle at which they will interfere with each other. Okay. So we said the intensity I was equal to I1, the intensity of the first wave at this point, and then the intensity of the second wave at that point, plus 2 into root of I1, root of I2 into cos phi or theta, how would you want to call that. So this cos phi, this phi is actually the phase difference between these two points these two waves at this point in space. If I take a different point for the same two sources, and if you take Q, then that can have a different phase difference. Phi can be different there. So then this intensity could be different from this based on the phase difference between these two waves. So this happens for coherent waves. So these were coherent waves, right? So these were coherent sources. So all the points in space will undergo this case, this condition. Okay, interference. So these are coherent sources, but for incoherent sources, the sources which are not coherent, then what happens is that the phase difference is not going to remain the same. It will keep changing. It will keep changing with time. At one point in time, you may have 30-degree phase difference, and at another point in time, you may have 45-degree phase difference, and at another point in time, something else. So this phase difference keeps changing. So what happens in the case of incoherent or non-coherent or incoherent sources? Incoherent or non-coherent, and this is changing, and since cos phi is changing, then you need to take the average of this. Cos phi is changing with time. So when you take the average of this, if as a sine function or a cos function, the average value of this will be 0. So effectively, then I is equal to I1 plus I2. And notice here, if this is if this does not have any phase difference component, then at every point in space, then you would have I is equal to I1 plus I2. Whether it is Q or P or any other point, the intensity is given by I1 plus I2. So you won't find, it would just be the sum of the intensities from these two. So you won't find an interference pattern if the sources are incoherent. Okay. Only when you have coherent sources can you find can you observe the interference patterns? Because for coherent sources, this will hold good. And if you take P, phi at P will not change in time. So I don't have to take an average. So this will remain the same. So this will obey this formula. And Q also will obey this formula. If phi is different for Q, then I may have different intensity for Q than I have for P. So this is what we have discussed so far. So this happens for all waves, and we demonstrated that with water waves. You saw it, you saw the interference pattern on the water surface. Okay, now we are going to talk specifically about light, the light waves. Now we know that light is a wave, but back in the 18th century or early 19th century, people were struggling with that idea, because people had bought the corpuscular theory from one of the greatest minds of all time, if not the greatest. It was Isaac Newton. Isaac Newton was a great supporter of the corpuscular theory. So if you're going to say anything against the theory, people were not taking it lightly. Can you be smarter than Einstein? Can you be smarter than Newton? That was the question which was on the back of everybody's mind. So when the wave theory was proposed, there was a lot of resistance from the scientific community. But it was Thomas Young, a British scientist, a physicist, in 1801, was able to prove that light is actually a wave. He was able to prove experimentally that light is a wave. The point is this: if you have two openings, if you have two holes, then if you throw balls through the holes and there is a wall, let's say there is a wall, and then you have cardboard. Okay, let's say this is a wall. The wall is here. Okay. Now you have a cardboard which has two holes. Now if you throw balls through these holes, then the balls will go and hit the wall here, and then the ball goes here. Okay, so how many other balls you throw through these holes, then they'll go hit there, hit here and there. So you'll only see two dots as marks on the wall. Keep throwing the balls through this hole. So if light is a wave, then if you send light through this hole and also through this hole, and when light falls on the wall, then you must be able to see only two bright spots. You cannot see anything else. They must see only two bright spots. But you don't see that. Okay? You see interference pattern if the light is from coherent sources. Okay? This is what Thomas Young proved in 1801. Now we know that light is a wave. So we'll do the same experiment in our thoughts, but then with understanding that light is a wave, and see what is going to happen on the other side of these two sources. Coherent sources. They must be coherent sources. If they're not coherent sources, you are not going to observe this. You will not observe interference patterns, but you will just see intensity being almost the same at every point on the wall. He said normal sources cannot be used as coherent sources. The reason being, if you take any light source, even if it is an incandescent bulb or even tube light, I'll probably explain that with tube light here so that you can understand it a little better. So what happens is that not all parts of the source are emitting light at the same time. For example, let me take maybe I'll take a small source. take source like this. We have already explained it before. This is, let's suppose this is light source. Okay, and let's say we take a point here. If you take this source, okay, it has million, almost like lots and lots of points here. I can treat this source as a collection of point sources. But we have to remember that all these points are not producing light at the same time. Okay, that there is a small time delay between these point sources on this practical source. So if this is producing light, maybe this is also producing light, and what can happen is that this may go to rest, like it emits light and then goes to rest for a very short period of time. So then at that time this is not present, and maybe the light from here is, this point is coming to this point, which is coming to this point in space. Okay, so now you notice, and previously the light was from this source and this source. Now it's from this source and this source. And after some time, I'm talking of very short period of time, which we cannot sense, but then a clock can sense. Okay, our eyes are not that sensitive, in the sense we have persistence of vision. So if something changes too fast, then we cannot differentiate that. So that's the thing. If the persistence of vision is against us, so we cannot do that with naked eye, but instruments can measure this. But now it's coming from a different source. Previously this was between these two, now it's between these two, and after sometimes it could be between this and maybe something else. You see, in all these cases, the path difference is changing. Previously it was between this and this, and now this and this, and now this and the third wave. So you see, the path difference is changing. If the path difference is continuously changing, then the phase difference will not remain the same. If the phase difference does not remain the same, then you won't see interference patterns. So for all practical purposes, no source is can be used as a point source. Okay, there is no point in using a practical source as a point source. It doesn't happen. Okay, because a practical source, even if it is very small, will have millions and trillions of atoms there. Then they must be sending light at different times. So the path difference would be changing, and you can never have the same length at all times from a practical source. So I want you to understand that. Okay. So I can't use this. So if I have one more source, then that also will be doing the same thing. So the path difference will be changing between those two sources. So how do I get coherent sources? Well, one way to do it would be this. Okay, I have a source. I have a point source here. Well, let's say I have a source this. Let me take this. I have a source. It has different number of point sources in it. Doesn't matter. Okay. So I take single source instead of taking two sources and then trying to figure out what will happen here. Clearly, interference will not take place because this length and that length will be changing. So you won't have interference patterns. But if you want to see the interference patterns, then what I'm going to do is I'm going to take this single source, then I'm going to go farther away from that source. If I go farther away from that source, then what happens is, let's say this becomes smaller and smaller. Okay, so this becomes smaller, something like this. If I go farther away, suppose I'm here. The light from here would be almost a plane wave for me. have gone too far away from this. I mean, this distance must be much bigger than the size of this object. Let's say the size of the object is say small s, and the distance, if the distance is say capital S, okay, the distance. If S is much greater than S, then this would be almost a plane wave here. Okay. Now, whatever be the source, the point that is producing that would have a plane wave here. Maybe it was this point that was producing it, or maybe there's another point that was producing it, another point. Whatever would be the point that is producing the light in that source would have a plane wave here. Okay? So now, if I take a plane wave, and if I send it through a very small opening, notice that once the plane wave hits here, then this is going to become a secondary source. So then at this point it's going to produce waves like this. And this will also produce a wave, this point. We use different color. Point. The wave. And they are in phase, right? Like it's clearly. So it's a single wave. So you see, now we can see indifference pattern. So then this distance will not change the phase. Why? Because these two are in phase. Whatever be that, whatever be the source, these two will be in phase because you are getting a plane wave here. So if they are in phase, then this phase difference is decided only by the distance now. We take this point, whatever point from there, because these two are in phase, because they derive from the same source, same point source I mean, because you've gone far away from the source. Since you've gone far away from the source, you get a plane wave. If you get a plane wave, then these two are in phase. If these two are in phase all the time, then the phase difference now depends only on the distance between, if I take a point, in this case point P, then the phase difference is going to be decided only by the path difference. So this is how I create coherent sources. I cannot have two different sources and produce indifference patterns, because those sources can never be coherent. Even if you take two red lights, okay, you take two red lights here, two red lights. This is red, this is red. Even if they produce the same frequency, but not here, I cannot have an interference pattern with those. Why? Because in this red light, this point may produce a wave first, and this point will produce a wave then. Okay. And a little later, maybe this will produce a light here, and maybe this will produce a light here. And now you see the path difference can change. And if the path difference changes, then the phase difference will not remain the same. So I need to use a single source, and I should get an almost a parallel wave, okay, a plane wave, should say a plane wave. Then if I take 2 points on that plane wave, then they will be in phase anyway. If they are in phase, and from that point forward, they are going to generate their own waves, because it's secondary waves, right? Because I'm going to take a point source here. I will block everything else. I will block everything else on the plane wave. So then I will make them as just a single point. Then they will produce their own waves, and when they interact, and when they superpose with each other, then you can have interference patterns. And again, the phase difference depends on the point in space now, right? So if it is P, then you will have certain path difference. If it is Q, you will have a different path difference. If some other point R, then you may have a different path difference. And that point difference will finally translate into phase difference, as we saw in our equations, and I can have an interference pattern here. Okay, so this could be bright, this could be dark, this could be medium bright, somewhere in between. Anything could happen. Any random point on space can have one finite value. Then when it has one finite value, then I can observe the interference pattern. I hope this is clear to you. But this is how you create two coherent sources. You create two coherent sources from a single source. You take a single source, a reasonably small source, okay, and let's say it has size S and a small size. But then if you go farther away from the source, then what happens is that you have a plane wave, and when you have a plane wave, then this point and this point would be in phase, whatever be the source here, they will always be in phase. It's a plane wave. And if you take 2 points on the plane wave and convert them into secondary waves, wavelets, actually you allow them to pass through a small slit, then it will produce a wave like that. If you produce a wave like this, then you can find interference patterns. So this is how you can find it. With this background, then we'll go study Young's double slit experiment.
Okay, so I'm going to try and demonstrate to you a practical experiment called Young's double slits, named after a bloke called Young who did loads of really cool physics. And this experiment uses 2 slits, as the name suggests, and this is really an amazing experiment, and you've got to do it yourself to really appreciate it, but I want to take you through it with this video first. If you're in my class, then you're going to do it next lesson yourself. We've got enough for you to do this experiment in pairs. So what does it involve? It involves this, which is a spirit level that's got a laser in it. So if I point that at the wall there, hopefully you can see it's a red laser. It's a nice low power laser that's going to be safe for us to use. Young did this hundreds of years ago, so he didn't have lasers, but they make our life easier, as you will see. We've got this thing here, which is a collection of double slits. So if you look really closely, you can probably see 4 slits in this slide. If I hold it up to maybe a white background, you see it more clearly. Each of those things that you can see there, oh no, that's lovely, that's focused really nicely. So you can see that each of those things that looked like one slit is actually a pair of slits, and the ones on the right are quite far apart, and the ones on the left are really close together. So these are double slits. What happens when the light passes through these 2 slits is that it spreads out. So when light passes through a narrow gap, it spreads out, it diffracts, and then the light coming from each of those 2 slits can interfere. So I'm going to shine the laser light through. I'm going to use the leftmost pair of slits because that's going to work best. So I'm going to shine this laser through a double slit, and then all the way over there, I'm not sure if you can see it, is a screen. It's a long way away, and you'll find out why that is shortly. So here we go. I'm going to turn the lights off. I'm going to turn the laser on, and I'm going to direct the laser through 2 of the slits. So the laser light is going through a double slit, 2 slits very close to each other. All the way down there on the screen you might just see some red. Now actually let me show you what it looks like without the double slit. Without the double slit it looks like a dot. Okay, let's go back. Now I've put a double slit in the way. So the laser light is passing through both of those slits, it's spreading out, it's diffracting, but when it gets over here, you get this very interesting pattern of bright and dark fringes. So it goes bright, then dark, then bright, then dark, then bright, then dark, and so on. So this is a two-slit interference pattern of light.
So this is how the experiment is done, Young's double slit experiment. Okay, so it's like this. You have a point source, or rather, you have a very small source, and then at a reasonable distance. Okay, you're going to have a sheet of paper or something, and you're going to make two slits on that sheet like this. You have a sheet of paper, and then you make two slits, two narrowly spaced slits. Okay. So these are the slits. Two narrow slits on the paper. So if light falls on this sheet, it's going to be blocked. It's completely blocked, and then one day the light will go through those two narrow slits. So now you have created the condition that we just discussed, the coherent sources. And on the other side, then you should be able to observe the interference patterns. Okay. So schematically, this is how it is done. So you have a source here, a single source. I told you, single source, and then at reasonable distance, then you're going to have two sources. Like you're going to split it. Okay, there is I'll probably do slightly more here. I think you get the idea, so we'll go with that now. So this is yes. So the plane wave, you're getting a plane wave. No, the distance is really great. Okay, you get a plane wave, and what you do here, then you got two slits. Okay, so you're looking at it from the top, and I'll call this as S1, and I'll call this as S2. So now the plane wave hits these two, and then the S1 and S2, these 2 points, these 2 slits, they become coherent sources now. So what do we see on the other side? Let's say I have a screen here. So this screen looks like this. So I have 2 slits here, like this. I'll put it narrowly spaced slits like that. Okay. Now this is the screen. Okay. And source is somewhere here. Okay. So the 2 slits and then the screen. But then I'm looking at it like this. From the top, I'm looking at it like this. So that is what is happening here. So this is the book I showed you, and these are the pens I showed you as slits. But then I'm looking at them from the top view. So S1, S2. Okay, and you can say that this, let's say, the distance between these 2 slits is D. Let D be the distance between these 2 slits. The spacing between the two slits. And let's say this distance, the distance between the slits and then the screen, is capital D. Now let me take a random point on the screen. Let's say, let me take some point here. Okay. So what would be the brightness of that? Would that be bright, a dark, a medium bright, or close to darkness? So that is what we are going to see now. Okay, let me take this point here, some random point. Let's say this is a point. I'll call this as P. Well, to find what is going to happen to this point, I need to find the path difference, right? Because This is going to produce a wave, this is going to produce a wave. So these waves will meet here. I'll say the wave will progress and then meet here. It will go and hit that point there. And this wave will also progress and then it will meet it here. Okay. So this is a wave travel. Okay. Well, you need to find the path difference, right now. If the path difference is n lambda, as we saw, then it will produce a bright spot. If the path difference is n plus half lambda, then it will produce a dark spot. If the path difference is something else, then you can get light of some intensity between these two values, from 0 to the maximum brightness. So that's some value you get. So it depends on what the path difference is going to be between this. So how do we find this? This point, let's say I'm looking at distance x from the center. So the location of the point is x distance from the center. So I got d is the capital D as the distance between the two coherent sources, the two slits, and then the screen, and small d is the spacing between the slits, and yes, x is a point, x the distance between the center and then the point of interest. So with this, I need to find the path difference. What is the path difference? The path difference is going to be S2p minus S1p. So the path difference S2p minus S1p. If this is n lambda, then I'll get a bright spot. If this is n plus half lambda, then I'll get dark spot. If it is anything between n lambda and n plus half lambda, then I'll get a point of a different intensity, varying intensity. So n can be 0, 1, 2, whatever, same. 0, 1, 2. Any value of n, so you get that. Okay. So how do you find the path difference from this graph? So S2p minus S1p. Well, I can use Pythagoras theorem. What is S2p or S2p squared? S2p squared is equal to this plus this square plus this square, right? But what is this square? That is d squared. Then what is this square? Well, that is x. And what is this? Well, if this is d, then this would be d by 2. So d square plus x plus d by 2 the whole square. So that gives me d square plus x square plus d squared by 4 plus 2 into x d by 2, then I get just xd. Okay? I get xd. 2 will cancel, I get xd. So that is my S2p whole square. What about S1p square? S1p square is going to be this distance plus this distance square plus this distance square. So S1p square is equal to, this is again d square. What is this? That would be, well, this is x and this must be d by 2, right? So this would be d by 2. This is also d by 2. The total is d. So that would be x minus d by 2 whole square. So what I'm going to get here? I'm going to get d squared plus x squared plus d squared by 4. Now I get minus 60. That's the difference. Difference is s1p squared minus s2p squared, or I should say s2p squared minus s1p squared. This is longer and shorter. It's going to be, if I take this and subtract this, then d squared will cancel, x squared will cancel, d squared 4 will cancel, and xt minus of minus xt is what I get. I'll get xt minus of minus xt. All other things will cancel. So that will give me 2xt. So s2p squared minus s1p squared is equal to 2xt. But I can expand this, right? A squared minus b squared form. So I can say that s1p plus s2p plus s1p, doesn't matter, into s2p minus s1p is equal to 2xd. Now what I'm interested in? I'm interested in s2p minus s1p. So then I bring this down. So s2p minus s1p is equal to 2xd by s2p plus s1p. Okay. So which is good. So s2p minus s1p, it's a path difference. This, what I'm interested in. This is equal to 2 times x into d divided by s2p plus s1p. Okay, now let us simplify this with some approximations. Let us suppose that I have gone too far from these two sources, s1, s2. Okay, my d is really long. If the d is really long, then compared to d, this d will be very small. Okay? And x also will be small. Let's say just keep it in mind. If you go too far, this s2p and s1p, if x is like too close to the central axis, then s2p and s1p will be almost equal, and they will be they too will almost be equal to d. If you're too far from the source. For example, like if I have the sources here, s1, s2 here, and if the wall is on the other side of the corridor, you know how long it is, it's too far. And if you want to see maybe like 1 centimeter, 2 centimeter from there, x distance on the wall, what kind of pattern it's going to form, then I can say I'm not really bothered about this s1p and s2p now. Notice it? The s1p and s2p will almost be equal to d, and because they are in addition here, this, this d and x would make little difference to this. Okay. So I would say, in that case, what happens is, if d is too far, if d is much greater than d and x, okay, what happens here is, that S2, this becomes S2p minus S1p is equal to 2xd by S2p can be taken as d itself, and S1p can also be taken as capital D itself. It's 2 form. Okay. So this becomes 2d. It's approximately, I should say. Approximately, this is the equation. So what happens is this 2 and this 2 cancels, and I am left with S2p minus S1p is approximately equal to xd by d. It's a wonderful result. But then this happens only when d is very far. And d is too far, then this holds good. We want you to understand that. As we said, when d is too far, then S1p and S2p reduces to this. S2p minus S1p reduces to xd by d. This is a path difference. The path difference is this. So, what is the condition for this point to be bright? Well, for this point to be bright, then this phase difference must be equal to the path difference must be equal to n lambda. So S2p minus S1p, if it is equal to n lambda, then P will be bright. P is bright when n lambda, or I should say xd by d is equal to n lambda. Okay. So the path difference must be equal to n lambda. Then P is bright when this xd by d is equal to n lambda by d. Okay. So, what happens at the center point? At the center, at the very center, you notice this path and this path are going to have the same length. In that case, then there is no path difference. So at the very center, then you are going to get a bright spot. If my P is this, if chosen P to be here, then this would be a bright spot. And do this way. So the center will be bright because there is no path difference. You see, same. You have S1p and then S2p will be here. So this part will be bright. Well, so for this is for all. Then again, the path difference is like 1 lambda. So from here, if you have path difference of 1 lambda, then you will have a bright spot. Then 2 lambda, then you have a bright spot. And 3 lambda, you will have a bright spot. 4 lambda, you will have a bright spot. Okay. So for n is equal to, for n equal to 0, 1, 2, 3 lambda. So the path difference is 0 lambda, you have bright spot. The path difference is 1 lambda, you have bright spot. 2 lambda, bright spot, bright spot. So, so what happens if the path difference is not n lambda but n plus half lambda? So for P to be, P is dark when this xd by d is equal to n plus half lambda. So if P is here, then you have bright spot, and if P is at some point here where the path difference is lambda, then it will be bright again. But then if P is somewhere in between these 2 points, where the path difference becomes n plus half lambda, then you will have a dark spot. So what you can see that you have a bright spot here, and in between you will have a dark spot. Then another bright spot, so in between you must have a dark spot again. So you will see bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. This getting stacked up alternatively. Okay. So you will go from bright to dark. The intensity will vary. It will become dark. Then from dark, you will go to bright. Then intensity again will vary. So from bright to dark, from dark to bright, from bright to dark. So you will see a fringe pattern. So you will have B here, and then you will probably have another B here. In between you will have dark here, and then you will have another B here, and then you will have dark here. Okay. So I mean the same thing will happen on the other side too. So we may have a B here, and somewhere here you will have dark, and then you may have next to B, and between B and B you will have dark. You will see bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. So this is the pattern that you will be seeing on the wall. So if you have slit like that, then you will have bright fringes and then also the dark fringes. But actually, the locus, like if for S1P, S2P, this path difference, it to be the same on that wall, the locus of the path difference, okay, it has to be hyperbola. If you think about it, you understand it. Because if you like let's say if I keep my hand like this, and then if I start moving, you see it's like kind of like hyperbolic thing is what I'll get actually. So on the other side, on the wall, then you will get fringes like this. Okay, the first one is like this, and then slightly like that, slightly like that, see, like this. So it's slightly hyperbolic is what you get. Then if you go further, much further, then you will have a typical hyperbolic curve. Okay, so let's not worry too much about it. But if you focus on any small area here, so it's going to look pretty straight. It's imperceptible. Okay, it is like this hyperbolic nature is very difficult to perceive. So, but if you are focusing on a very small area on the wall, then you can see that like they're pretty much straight area. So you will find, for all practical purposes, I will say that you will find something like this. You will find this on the wall. You will find dark, bright, dark, bright, dark, bright, bright. That should just it's like this, but then for all practical purposes, you can say that you get dark, bright, dark, straight lines on the wall. Okay. This again, this dark is again, say like n is equal to 0, 1, 2, 3. So now the question is, can I find the fringe width? What is the fringe width? That is this length. Okay, if I take this, it's going to be this length. Okay, so one bright spot to the next bright spot. So you have a dark spot in between. So bright, dark, bright. So that's the fringe width. You've got one fringe. Because that's a pattern which is getting repeated on the other side. Okay, so how do I do that? Well, it's very easy to do. When will I get the first bright spot? when this is equal to 0. And when will I get the next bright spot? Then when n is equal to 1. When n is equal to 1, then I get lambda. So from the center to the next one, then I have just to subtract this position. Let me find the position of x now. Let's say, what is the position of x? What is the distance x? Position of point P. That is distance x. So distance x from this for bright, x is equal to n lambda to d by d. From this expression, I am getting that. So x will be 0. At x is equal to 0, we will find a bright spot, which is like very much here. The next one would be lambda d by d. The next one would be 2 lambda d by d. So here you will have bright. What is x? X is distance between the central axis and then the point. If the point is on the central axis itself, then you will get a bright spot. In that case, x will be 0. If the point is away from the central axis, then n can change. And if you want to find the first one, then you can say that x, this is x1, I'll say. Okay, let's say my x0 is equal to 0, right? It is 0, bright spot, very much there. And what is my x1? x1 will be n is equal to 1, so lambda d by d. Okay, what is the fringe width? The fringe width is going to be the position of x1 and then the position, I should say, the position of P here and then the position P here, so this distance, that is your fringe width. So that is what is called as, say, x1 minus x0. The distance between the first bright spot and then the next bright the distance between two bright spots. In this case, I have taken the central bright spot and then the first bright spot. So this is equal to beta, which is what I call as bandwidth, is equal to lambda d by d minus 0. So bandwidth is equal to lambda d by d. Okay. This can also be obtained for a very general case. Even though I have taken the central bright spot and then the next bright spot, the first bright spot, you can do it for any two bright spots. How? Well, let me take xn is equal to n lambda d by d. Okay. N can be the first, the second, the third, the fourth, the fifth, whatever it would be. Then the next one, the next bright spot would be the n plus 1, right? So that is equal to n plus 1 to lambda d by d. So the difference between this point and this point is going to be xn plus 1 minus xn is going to be equal to n plus 1 lambda d by d minus n lambda d by d. And if you do that, then you will get, this is actually the bandwidth, right? So bandwidth is equal to lambda d by d. So this bandwidth is given by this expression, beta is equal to lambda d by d. So the farther you go, then the spacing would be greater. You can clearly see the bright and dark spot. And then if you narrow the split, the distance between the slits are too close to, the closer the slits are to each other, then also you can see a big bandwidth. And if you use a bigger lambda, if you use red light instead of blue light, then the spacing would be more. So the bandwidth would be more if you use red light for the same experiment. I may use blue light, then I may get a certain bandwidth. Instead of blue light, if I use red, then I get the same pattern, but then the bandwidth will be greater. So the bandwidth of the interference pattern depends on lambda and then the distance between the slits and the screen, and also the spacing between the slits. These are the things which decide the beta. Okay. So this is for illustration, purpose of illustration, but this is the actual condition. I want you to agree. Hope you understand this. Okay, now let's do some example problems. Very simple. Problem 10.3. Two slits are made 1 millimeter apart and the screen is made 1 meter away. What is the fringe separation when blue-green light of wavelength 500 nanometer is used? So you do the Young's double slit experiment. This is 10.3. This is Young's double slit experiment problem. So here the separation between the two slits, this is S1, this is S2. This separation D is given and this D is also given. Okay. And they want you to find the fringe width. The fringe width beta is given by lambda D by D. So only like the fringe width will increase as the distance increases, and fringe width will also increase as the separation decreases between the slits. So this is the expression. So what are they given? They have given that D is 1 meter, and then the separation between the slits D is 1 millimeter, and lambda is 500 nanometers. So blue-green light is what is used, so you get 500 nanometers. That's the lambda. Okay. So how do you find the bandwidth? Very easy. The fringe width. Beta, lambda is 500 into 10 power minus 9, and then D is 1 meter, so divided by is 1 millimeter, so 1 into 10 power minus 3, so this is minus 6, so it's 5 into 10 power 2 into 10 power minus 6, it will be 5 into 10 power minus 4 meter. So bandwidth is actually 0.5 millimeter. You see, it's very small. So in half a millimeter, you will find the bright, like half a millimeter is the distance between the bright and bright spots, or dot and dot. So it's very small. So if you keep it at 1 millimeter, 1 meter, the scale is 1 meter away from you, and then the slit is like the distance, the separation is 1 millimeter, then the fringe width that you see is going to be like this. Hope this is clear to you. It's not very difficult to do this problem. Hope this is clear to you. Okay, let's do 10.4. I've written 10.4 on the board. Let's read that. What is the effect of the following on interference fringes in Young's double slit experiment? YDSA is Young's double slit experiment. Okay, 1. Screen is moved away from the slits. Well, we know this. Okay. So what's the bandwidth? Bandwidth is given by lambda D by D. So the screen is moved away from the slits, then D is increasing, which means the bandwidth will increase. So this we already discussed. Second, a monochromatic source is replaced by another monochromatic source. So what does it mean? Monochromatic source is a light of one color, is replaced by another monochromatic source. Maybe you had red before, now you have blue. So what is going to happen? Again, you have to use this formula. So beta is equal to lambda d by d. So d doesn't change, d doesn't change. These two things don't change. You have just changed lambda. So depending on the lambda, then the bandwidth will change. Because the lambda is changing here, the bandwidth will also change. So you will have one bandwidth for red, another bandwidth for yellow, yet another bandwidth for blue, and things like that. So this is also discussed already. Then separation of the slits is increased. Again, use this. Separation of the slits, meaning small d, the lowercase d, is increased, meaning the bandwidth will reduce. If this increases, this should reduce. So that is 3. Then fourth, source slit is moved closer to the double slit plane. Okay? So this is what we discussed before we did YDAC. Okay? Well, this is S1, S2, and then this is the screen. So this is a double slit plane, right? S1, S2. So now source slit, I said you have to keep it further away so that you get almost parallel wave from where you derive the other two sources. Okay? So suppose this source slit, if this is moved closer to the plane, then clearly you are not going to get plane waves. Like it's not, the wave that reaches here will not be a plane wave. It will become more and more spherical. And then it's quite possible that at some point the interference pattern will stop, because light from two different point sources on the source could cause this for the superposition, resulting in the interference pattern not appearing. Okay. Let me put it this way. If you bring the source closer, then it is very difficult to keep S1 and S2 as coherent sources. If S1 and S2 are not coherent sources, then you won't get interference pattern. So actually the formula for that is S, the small s by capital S, must be less than lambda by d. It's like this. That small s is size of the source, and this is actually the distance between source and the slits. Okay, this S1, S2, source and S1, S2. If this is the source, the small s is the size, and the capital S is this distance. Okay? So this formula is this size divided by this distance must be less than lambda of the source, and then the separation between the slits. So if you are bringing it closer, then what happens is that you are actually reducing this S. So this is increasing. As it's increasing, you may reach a condition where, or you may reach a point where this condition is not met, then interference pattern will disappear. This point. Okay. So that is about the fourth one. And then the fifth one is width of the source slit is increased. Again, the source slit. If the width is increased, you are actually increasing this S. Small s is increased. So it's quite possible for you to lose the interference pattern if the width is too big. So big that S by S is less than lambda by d, then the interference pattern will vanish. Only when this condition is satisfied can you see the interference pattern on the wall. So, and that is because as you increase the size, then waves from different point sources on the source can reach here, resulting in rendering these two sources as incoherent. That can happen. That's the reason. So, is that? And sixth, monochromatic light is replaced by white light. Well, yeah. If you use monochromatic light, then you have only one lambda. But then when you use white light, then it has other lambdas. Okay, and the visual range, you have the 7 colors, they all have many different lambdas actually. So what will happen in this case is like you will have a bright spot for red, a bright spot for blue, a bright spot for yellow, and again a dot spot for red, and then the dot spot for blue. So you have different bandwidths. So with different bandwidths, the overlap will take place. So you will see a rainbow like picture on the screen actually. I'll share a video which actually deals with this condition. So you can see like when you use sunlight, like which is white light anyway, which has all the colors, then what happens to your double slit experiment? You'll have the same thing happening, but then the same thing will be happening for different colors. So that's what you'll be seeing. Hope this is clear to you.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's 2 openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom of the box?
The obvious thing you think you're going to see is you're going to see two lines.
2 lines on the bottom of the box. 2 bright bands.
2 little lines.
Yeah.
I think it'll be one line instead of 2.
I could expect to see the whole box lit up.
It'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, 2 either side.
The 2 on the outside are multicolored, and the one in the middle is just white.
It's kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
It's like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
2 slits.
2 slits. I can't believe. That's incredible.
But all we're doing is we're putting a light through 2 very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see 2 bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. this pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.